realm of superficiality and take the big picture in.
We left off the big picture last time, looking at evidence of impacts all across North America, specifically in the United States. And Randall has just gotten back a week ago, 2 weeks ago, from a tour of the Bonneville flood area.
Yeah, 2 weeks ago. Yeah.
2 weeks ago. And there's been some exciting new discoveries. There was a lot of footage taken, a lot of content that's being created from it. And it's being edited, but it's going to be something that is pretty mind-blowing, Randall. So what did you discover? Give us a sneak peek before we go through it more in depth on a later episode.
Well, it wasn't so much like any mind-boggling new insights, but it was definitely a deeper appreciation and additional questions about what exactly happened. First point is, it had been the last time I made a traverse of the Bonneville flood route was 25 years ago.
Wow.
So I was vague, and I was definitely in need of a refresher. So one thing that impressed me this time that I didn't my first time, I pretty much immediately left Salt Lake City and headed north and began following the route of the breakout flood. Now we've talked about, we did a whole episode where we're talking about the Bonneville flood. So not to go over all of that again. If people haven't seen that, go back and watch it, right? And then what I'm talking about here will make more sense. But one of the first thing that impressed me was the vastness of Lake Bonneville. The realization of how extraordinarily huge this body of water was. I mean, it was incredible. And, you're driving around in the deserts there, and you're realizing that 15,000 years ago, you'd have been at the bottom of 1,000-foot deep lake. You're in the desert, right? Dry as a bone. And 15,000 years ago, you would have been at the bottom of a lake 1,000 feet deep. Obviously, something changed. Something, I mean, so as it is now, the environment of this area in Utah does not support the existence of hardly any lake at all. Great Salt Lake is the remnant of Lake Bonneville. It varies from season to season depending on the amount of rainfall, 20 to 30 feet in depth. So, I mean, it's minuscule compared to ancient Lake Bonneville. So clearly, you've got, I mean, there's no way you could have Lake Bonneville without having an extraordinarily amplified volume of rainfall or precipitation, right? Because here's the thing. Right now, Great Salt Lake will fluctuate in area. As it gets deeper, of course, its surface area gets wider. But the more surface area you've got, the more evaporation you're going to have. So there's this kind of equilibrium point where precipitation and inflow into the basin is going to equal the outflow through evaporation, right? So if you have more rainfall, the lake can deepen. If you have less rainfall, you go into drought conditions, the lake can dry up. There are many what are called playa lakes throughout the southwestern deserts and other deserts of the world, right? But the ones I've visited have been in the southwestern United States. But a playa lake is basically a lake basin that is oftentimes just a dry basin. And then in years with the more precipitation, it'll actually turn into a temporary lake. And then there's this fluctuation. A little bit more rainfall, you got a lake. A little bit less rainfall, it evaporates away. And it might be a dry basin for 5 years or 10 years. And then you have a few years of augmented rainfall, and then it turns into a lake, right? But I don't think that's what Bonneville was, because for one thing, the Lake Bonneville was so huge. And as it grows, my point here is as it grows, its surface area is enlarging as well. And so it's going to increase the rate of evaporation. but the ratio of inflow to the lake from whatever source had to vastly exceed the amount of water lost through evaporation. So in order for that to happen, clearly the implication is you've got an environment that's just drastically different from the one that's there now. So what does that imply? Well, there's all kinds of implications for that. For one thing, I mean, it's just one more piece of this puzzle of climate change that is supposedly, we're constantly being told over and over again, is settled. And there's now a consensus about the whole question of climate change. But just going out and spending a week looking at this and pondering the implications of it just completely undermines that false perspective. No, it's not settled. There's all kinds of questions we've got about climate change, because clearly we're talking about a major climate change from the climate regime that could support 1,000-foot deep lake to the climate regime now where that lake is gone. And you've got, I mean, while you're there, look up the Lake Bonneville volume of water, and then the surface here. I think the volume of the water will be somewhere around maybe 5,000 cubic miles, if memory serves me correct.
Yep. No, 4,750 cubic kilometers. So 11
cubic kilometers. I said miles. Cubic kilometers.
1,100 cubic miles. Around 1.2 quadrillion gallons.
1.2 quadrillion. So say that again, about 1,500 cubic, 1,100 cubic miles.
Exactly.
Yeah, that's a lot of water. I mean, just try to imagine 1 cubic mile of water. You're standing there and you're looking at an ice cube that's 1 cubic mile. Well, that means it's a mile high, a mile wide in both directions, and you're standing there looking up a mile, right? That in itself would be a big, pretty healthy lake.
Oh, yeah.
And now what'd you say, 1,100 of those?
Exactly.
And that was the volume of Lake Bonneville.
It's massive.
Right.
And
now,
how big is Salt Lake, the Great Salt Lake?
Let's look that up. In fact, I was just going to ask you to look that up.
The Great Salt Lake holds 18.92 kilometers compared to the 4,750.
Okay, so 4,750, we're dividing by, what was it,
18.92.
0.92. Okay, so Lake Bonneville was 250 times more voluminous than Great Salt Lake.
Wow.
So if you're going to call Great Salt Lake, what do you call Lake Bonneville? That's 250 times bigger. I don't know.
Do we have a good term for that?
Ultra great.
Ultra great. The greatest Lake Bonneville.
But it was even relatively small compared to Lake Agassiz, which is we're going to be talking about.
Is that what we're going into today?
No, I don't think we'll have time to get to Lake Agassiz today. And Lake Agassiz will deserve probably its own, a whole episode devoted to Lake Agassiz.
So where are we looking today then? What are we looking at?
Let's do this. Okay, I'm talking about the impression that I had of the vastness of Lake Bonneville, and the thoughts that I was having in connection with that is what I've just shared with you, and pondering what kind of environment would be necessary to support a lake like that in those dry desert basins of Utah that we see right now. So that was certainly one of the things that I came away with. And I think probably the answer partially is that it had to be a very quick phenomenon, right? In other words, I think what we're seeing there is precipitation over a fairly quick period of time temporarily completely overwhelmed any rate of evaporation or volume loss due to evaporation.
And how long is a quick period of time, would you say?
Well, I don't know. I'm not thinking many, many years, though. I'm thinking probably months.
Months,
if not weeks.
And this would be for Lake Bonneville to first appear.
Well, no. it's almost certain that there was a lake there. Okay, what I would surmise is the model looked like this. There was a lake. It was a freshwater lake. It would have been south of the glacial front, which was, up there in Washington, northern Idaho, and so on. So it's south of the glacial front. However, obviously during the late glacial maximum, that region of the central region of America is going to be much cooler than now. It's also likely that the jet stream has been diverted to the south. So it makes sense from that standpoint that the southwestern deserts of the United States could have actually been green and relatively lush, including the Basin and Range province of Utah and Nevada, right? So there was probably a lake there, and it was probably significantly larger than Great Salt Lake because it wouldn't have been a desert.
Mm-hmm.
How deep was it? Maybe 50 to a couple of 100 feet deep, right? The question is how much time and when, and again, I've come back with a lot of new information and studies that I'm trying to digest right now. But what it's appearing like is that there were a couple of episodes of rapid filling followed by decline in lake levels. It seemed like it was a very dynamic lake. And then there was a final stage where it rose up to this maximum height, which was about just over 5,000 feet above sea level. And at that point, if you look at the maps of the lake, there's the entire basin and range of Utah and Nevada is an internally isolated basin. It doesn't have outflow to the ocean. However, during this Bonneville flood, there was a temporary large-scale outflow to the ocean because the water rose, and when it hit just over 5,000 feet above sea level, on the northern rim of the lake, there was a low point. Obviously, when the water rises up to that low point, that's the first place it's going to start spilling over. Now, there's a study that I've just read since we did the tour suggesting, here's the model. Imagine a hard bedrock sill, even like granitic type metamorphic rock, hard rock sill, and then you've got 350 feet of more or less alluvial, soft, not completely lithified material that has been outwash from erosion off the adjacent mountain ranges. And it's relatively young compared to that hard bedrock sill. So now the question is, the water in Lake Bonneville rises up. And at some point, it is now just above 5,000 feet above sea level. It gets equal in elevation to the surface of this fan, alluvial fan. So it starts flowing over. Now the question is, how long of a time elapsed between the level of the lake coming up to the sill or the top of that alluvial fan and the bursting out of that lake, discharging 35 million, 40 million cubic feet per second? Because that's a hell of an event there. So now, in reading the reports, it seemed like the idea was that for some period of indeterminate period of time, it was a relatively stable situation with the lake level being that high and then a river flowing out that might have been what we would think of as a normal sized river, right? Now, the question is, how do you get from there to the flood, and how long was it that there was the water level up to that height, a normal type river, and the outburst of the flood? One of the studies was suggesting there was an earthquake, and the earthquake caused the failure of the alluvial dam. That makes sense, right?
Yeah.
But what doesn't make sense to me is the assumption that there was some protracted period of time between the lake level getting that high
Just
and there being like
and then
and then you've got a normal river, for hundreds of years or whatever. But again, then you have the problem is sustaining that lake level again. And now if you still have that open, what was the surface area of Lake Bonneville at its? I'm going to get these in my head so we don't have to look them up all the time. Surface area, Lake Bonneville, 20,000 square kilometers?
Square miles.
Square miles. Okay.
20,000 square miles, 51,000 square kilometers.
Wow, 20,000 square miles. That is a lot of surface area. I'm going to just see if we turn that into 20,000. If that was a square, that would be a square, 140 miles on a side.
Wow.
So that was my point. That's what I came away with, was the sheer magnitude of the basin, the area of Lake Bonneville, right? Now, if there's an elapse of time between its rise to the 5,000 foot above sea level datum and its overflow, how do you maintain? How much rainfall has to come every year to maintain that level of the lake? See, I have to think through this because I'm trying to make sense out of it, and it's not adding up somehow. This is why I'm thinking I'm again circling back to a singular event of extreme rainfall that might have raised the lake level the last 300, 400, 500 feet. See, there may have been a big, impressive lake there, and that would make perfect sense to me that you would have had an impressive lake in the basin already, right? Because of the climate of the late Ice Age, right? It would just make sense that being cooler, I'm thinking, and the fact that a mile and a half thick, or maybe more than that, thick ice sheet is theorized to have shunted the jet stream southward by, I'm not sure how much, 1,000 miles, maybe more. Which, of course, the jet stream is going to bring precipitation with it, right? So we know that, like, ENSO cycle is connected with the jet stream and the movement of the jet stream. So, for example,
what is that?
The jet stream?
No, the ENSO cycle.
It's the southern. Let's see. It's a Spanish word. So it's the southern. It's called EN Southern Oscillation. Just look up ENSO. I mean, again, I should know that, but I think the EN is
Southern. Yeah. El Nino.
Nino Southern Oscillation. Thank you.
Yeah.
Okay, so El Nino Southern Oscillation can bring moisture. If it shifts to the south, it'll bring moisture. For example, like if it's going over the Mediterranean level, I believe Europe will be dry. If it shifts to the north, Europe will get a lot of precipitation.
Yeah, and it says it happens in 2 to 7 year cycles. Yeah, this cycle, which typically occurs every 2 to 7 years, involves 3 phases: El Nino, La Nina, and an ENSO neutral phase. El Nino is a warm phase, La Nina is a cool phase, and the neutral phase is a transition between them.
Right. So that's one of the cycles that causes climate change more on a more micro scale. But
so
clearly,
would you think that the mass pluvial period that could potentially, if it was one event that had this happen at once, are you saying that it could happen naturally because of the ENSO cycle, or would it be something that caused?
No, because what we're seeing, the ENSO cycle is operational as we speak.
Right. So this would have to be caused by something like if there was an impact and it threw a bunch of stuff into the atmosphere, and the moisture had to come down somewhere. The water had to come back down.
I'm having a hard time visualizing something that's not catastrophic. And that you've got some prolonged extreme pluvial phenomena going on that would have raised the lake level. But see, my problem is the assumption that span of time between the lake topping out, how much time elapsed between the topping out of the lake at its highest elevation and the breakout of the flood, say at 35 to 40 million cubic feet per second. That's the thing I'm trying to understand, and I don't know. I don't know. Is it going to be a matter of weeks and months, or is it a matter of years, centuries? I don't know. Some people who've been worked on it think it's centuries. But then to me, that raises questions like, okay, hundreds of years, the lake is at that level? Well, let's talk about what kind of climatic regime is going to be necessary to sustain a lake of that size. And I don't know what that would be. Maybe I'm missing something here. I'll admit my understanding of climate change,
So
while
it would
more
just
than
have to be
most
a
people.
lot of rainfall or an equivalent amount of rainfall or inflow to the amount of evaporation that there is. And that would be equal to a lot, if I'm understanding you correctly.
Well, yeah, I mean, the amount of loss through evaporation has to be just almost microscopic compared to the input into the basin from whatever source. But one study I recently read said, I think they were estimating that 3.3% of the lake volume was contributed by melting glaciers. 3.3%, or in that ballpark.
Okay.
So if that's the case, then where did the rest of it come? It had to have been rainfall and precipitate. I mean, is it snowfall? Well, I'm obviously could be snowfall, but
And this is the total Lake Bonneville, including the lake that was there already that it filled up, or is this what was added in volume in addition to the
no, this would have been
pre-existing
the total
lake?
volume at its maximum. So if I was going to create just a hypothetical scenario based upon what I know, which is still limited, although I'm definitely learning more. I mean, I've got new studies now that I'm reading and having brought back, all the new observations. Yeah, I'm advancing my thought about about Bonneville to the next level. But what I would think would be something like this: that there was a lake there, and it was a pretty substantial, impressive lake. I mean, if there was a lake there that was 200 feet deep or 300 feet deep, that would be a pretty impressive lake, right? And that would be, in my mind, completely realistic with what a realistic climate regime might be during the late glacial maximum, right? Why? Because of that, the shunting of the jet stream further south. So you probably got the jet stream moving over the whole basin and range. So it's bringing weather with it. It's bringing the rainfall with it, right? So, and it's also cooler, more rainfall. It's likely, and we know, I mean, for all kinds of studies, I mean, that there were forests and there were, it would have been a sort of a mosaic, it looks like, but it was not a desert like it is now. So the climate changes at the end of the last ice age, it seems, were associated with this transition from this former environment into the desert environment that we see there today that does not sustain huge lakes. So then I guess the question in my mind that I keep going over and over again and iterating and reiterating is, what happened? Where do you get that much rainfall that you can completely overwhelm that ratio, completely tip that ratio so far into the onto the accumulation side compared to the evaporation side? And it just had to have been an enormous amount of rainfall. So again, we go back during the Ice Age, there was probably some pretty substantial lakes occupying the basins of the Basin and Range province of Utah and Nevada. Then what it would seem like to me, and this is an idea that needs to be thoroughly tested before it's accepted, but the idea would then be is that towards the end of this, somewhere, in the last few thousand years of before the transition out of the Ice Age, somewhere within that window, there would have been intense pluviation, intense rainfall, filling that lake up to its brim. And at that point, it's flowing over the alluvial dam on its northern rim, right? Interesting. We got, drone footage and new imagery and everything of that whole outlet there. So now the question is how much time elapsed between the maximum full pool of Lake Bonneville and the outburst of the flood? And I don't know the answer to that.
Well,
I would lean towards thinking that it was a very short-lived event. And now what I'm going to do is I'm reading and rereading the new evidence that there was an earthquake. Because it seems to me that if you have a rapid filling, I mean, look at the volumes of water we're talking about here. And we know from looking at the shorelines of Lake Bonneville are not level, they're tilted. Why are they tilted? Well, because once the lake was removed, the land has risen. And it's risen more in the deeper parts of the lake than in the shallower parts. So just think of a simple profile like this, a concave profile, deeper in the middle, shallower on the rim. So now the lake is in there. Then you remove the lake and you start having isostatic rebound. Now, again, you've got a basin. When the water's there, it's going to be level. Remove the weight of the water. It now starts coming back, rebounding. What's going to happen to the water level, the shoreline? Well, the shoreline is going to come up and it's going to be tilted higher in the middle, isn't it? Mm-hmm. Makes sense, right?
Yes.
Well, that's what we see. We can see that in the shorelines of Lake Bonneville. They're tilted. That's because of isostatic rebound after the tremendous weight of this huge volume of water was removed, right? That isostatic adjustment could certainly be associated with seismicity. And we're seeing evidence of that all over the place. The other thing, and I think we talked about it on one of the episodes, was the glacial forebulge. So let's say you've got a level field like this, and you put a weight on it. Well, it's going to depress in the middle. Watch my hand when I push down, like on my knuckles. It'll depress in the middle, but then look what happens at the edges of my fingertips.
Curve up.
What you're seeing there, that's your glacial forebulge. So that's the uplift of land just beyond the rim of the glacier.
Okay.
Of the ice. So now you got the glacier forebulge, and what happens when you remove the weight of the ice? Look, middle comes up, and it relaxes and goes down. The glacial forebulge drops. People don't think about that stuff.
Yeah.
that there's actually an elasticity to the Earth's crust that manifests in these isostatic adjustments that take place. But they do, and they're well documented. So
this might be a missed question, but is there a threshold to the size of a glacier and glacial forebulge even being possible? So, for example, if it's a smaller glacier, is the Earth's elasticity threshold higher so it wouldn't have any forebulge on a smaller glacier, and then you reach a certain size, so then there is?
Well, now we're getting into structural geology and the discussion of rheology, which is a complicated subject, and it looks at exactly what you're talking about. What is the elasticity? What is the viscosity of the plates and their movements relative to one another? And there's a lot of variation in there. So I think you'd have to address a question like that on a case-by-case basis.
Yeah, that makes sense.
Yeah.
Depending on what the Earth is made out of in that area.
Correct. Yeah. So there's a lot of unanswered questions, but they're questions that need to be asked because without understanding our own catastrophic past, we can't understand our past, period. And if we don't understand our past, we have no hope of understanding our future. So there we are. We're stuck in the middle, which is the present, and we're not explaining anything. But the present is loaded with the clues that we need in order to reconstruct. In a sense, what we're doing when we're going out in the field like this and documenting these features and this kind of evidence is we're sort of like re-engineering. We're reverse engineering these catastrophic events. we're trying to work backwards. We can see the evidence in the field. We can see the shorelines. We can see the fan deltas. We can see the boulder bars. We can see the cataracts that are there now, that are the imprints, the after effects of these events. So we have to start with what we've got now and then begin to work backwards, piece by piece, reconstructing these events. The problem is that you get a sense you've got to I would call it a boundary problem. And the boundary problem is, to understand an event, you have to establish some kind of boundaries. Now in nature provides us boundaries. Yeah, there's a watershed divide. Okay. Rainfall falls on the divide here, and it goes to this watershed, and over here it goes to this watershed. But when we're looking at like temporal events, we have to provide boundaries, and we have to provide geographic boundaries, because if we're trying to understand what's happening in, say, the basin and range, or what's happening up at Red Rock Pass at the time that the flood burst out, right? Mm-hmm. Well, we have to put these sort of artificial boundaries, right? And that's what they've, like, for example, done with the Missoula floods. They put boundaries on it, and if I pull up this graphic, which is showing the late glacial maximum and the Missoula floods, they have a nice box around it, right? And what's happened is you've got this box, and within this box, you've got all the studies, but they're pretty much artificially not going outside that box. And I don't think you can fully understand what happened until you go outside the box. Again, you know what it comes down to? The big picture.
Yeah.
You got to have the big picture. I'm tempted to pull.
Pull it up.
I will do that right now then. Okay, here we go.
And that's I think we talked about isostatic rebound once before, but glacial forebulge, I think, is a new term.
Probably it is. Well, this illustrates what I was talking about. So, sort of the standard view now is, you want to learn about the Missoula flood. Well, you don't need to, everything you need to know is in that box. See, I don't agree with that. I think if we want to understand what happens inside the box, we also have to understand what's happening outside the box, because that box isn't real. I mean, yes, nature does provide a sort of there's a reality there. If I was to zoom in, we would see that, for example, this is most of the Columbia watershed right here. However, even during this period of time, from now, there's no ice. All of this ice is gone. It's just limited to isolated montane glaciers or mountain glaciers. But this huge, vast amount of ice here that's as big as Greenland ice sheet and Antarctica ice sheet put together, that's how much effing ice we had over North America during the late glacial maximum. All that ice is gone. Why? Because it melted. When it melted, you had huge amounts of meltwater flow, ultimately wanting to get back to the oceans, and that's where all of this meltwater went, was back into the oceans. Sometimes I get questions, and people, I don't know if they're, I would, if a 7-year-old asked me this question, I wouldn't be shocked, but I know that this is coming from an adult. And I've gotten asked this question multiple times, like in online comment sections. Well, where did all the water go? You had all this melting. Where did the water go? Well, where all of it goes ultimately. I mean, what, did you grow up inside a box? Did you never get outside? Where do you think it went? It went into the oceans. I've been really, what? Where did all the water go? Well, I don't know. No, that's a mystery. We don't know where it went. Well, we do know where it went. All went into the oceans, and one of the things we're going to be looking at here as we move forward is how the water returned to the ocean.
Right. And we've been looking at some of that as well. Some of the traces of it, looking at.
But see, what people don't realize is the magnitude of the after effects. We're like microbes living on top of this gigantic phenomena. And it's so gigantic that we as mere microbes we don't see it. It's too big. And that's why it's necessary. I'll say this. It is necessary sometimes to draw these artificial boundaries, right? You have to try to understand. But then as you go through it and you learn about it, I mean, I started really studying the Missoula floods in the early 1980s. In the 90s, started making my first tours of that landscape, and I've been back. I've lost count, 25, 30 times, exploring every nook and cranny of this landscape, and realizing on every trip that no, there are some huge gaping holes in this box here. And if we're going to understand to repeat myself, if we're going to understand what transpired inside that box, well, we have to also understand what was going on outside that box. Because nature didn't really recognize. If you have an enormous amount of rainfall coming in, moving over, if the jet stream is moving, being shunted to the southward because of the formation of this huge ice sheet here, well, that jet stream it's ignoring this box. It doesn't recognize that box. Oh, we can't go any further south. There's a box there. No. So the first thing is Harlan Bretz is looking at Washington. Let's just go to another map. So initially, here's the basalt plateau. This is what J. Harlan Bretz was studying for 25, 30 years, right? Discovered these features called the channel scablands. And he's looking at this area right here. And all of his critics are saying this was what the argument boiled down to. Well, you say all this stuff, all of these features that you've documented were produced by giant catastrophic floods. Well, what was the source of the floods? And he didn't know, but he thought that the floods were coming from melting glaciers. Let's go back one. If we go back to here, you'll see that the southern margin of the Cordilleran ice sheet just breaches the northernmost rim of the basalt plateau. Now, and let me take a little quick diversion before we move on. So people, look over here. You see my cursor? That's Yellowstone Lake.
Mm-hmm.
Under Yellowstone, right here, there's an active magma plume rising up, right? That creates all of that volcanic volatility that's so recognizable, associated with Yellowstone. Okay. If we go back and we start dating, we have basalt all in here, and we have basalt floor here. So down here at the bottom of this, you see Lake Bonneville Great Salt Lake is down here.
Now we can't see your marker anymore.
Oh, sorry. Right here it is.
Yeah.
That's Great Salt Lake. And the outflow path was right up. Let's see. It was, I don't have the resolution. It was right up. Yeah, it was right up here. If you can see. The low point is this one place. It's, Red Rock Pass, it's called. The flood burst out and it flowed across the Snake River Plain up to here. And this right here is Hell's Canyon. And this is the deepest canyon in North America. It's deeper than Grand Canyon. Yes. And then the Snake River flows out this way. You can see it right here. And then it's a tributary to the Columbia. And right here at the Tri-Cities area, just above Wallula Gap, which we've talked about, the waters of the Snake flowed down the Columbia, through the gorge, across the Cascade Mountains here, and then discharged right here. There's an eroded valley right here that was cut by the huge volumes of flood water gushing off the Columbia Plateau here, coming out, and then out here you don't see it here. We could pull up a Google Earth image, but out here under the water is a huge fan delta. That is the material that was being washed off the continent, washed off the plateau, and carried through the gorge and then dumped out into the ocean. Okay, now this is what's interesting. Look at this area closer right in here. This is a very chaotic area, and it's riddled with things that are called feeder dikes. These are big fractures where lava has come up, magma has come up and discharged out. And here's what you got to understand when you're looking at this. You see the great arc of the Snake River Plain?
Yes.
Okay. I'm going to use my hand here. You can see my hand, right?
Yes.
Okay, so imagine you've got this. Maybe I could get something here that might serve. Here, this is my spoon. Excuse me. So let's say my spoon is a magma plume, and this is the crust. Excuse me. This is the crust of the earth, right? So you've got this hot flame, like some kind of like a geological
Torch.
acetylene torch, right? You got the crust moving over it, the rock moving over it, and that rock is being melted by the heat. Now, as it's moving over, it's not moving in a straight line. It's actually moving in an arc. Now, the age of the basalts have been measured to be around 16 to 17 million years old. And for about 10 million years, let's say from 16 or 17 million years ago down to 6 million years ago, there were these huge outflows of magma from these feeder dikes that are in this area right here. Well, what you can see is if we had a cosmic drone footage of the Earth and we could replay it for the last 16 million years, what we would see is that this area in here moves back along this arc, and that 17 million years ago it was sitting right on top of this plume. Is that making sense? Or can you begin to see the phenomena here? So because that lava that's coming out and forming these tremendous layers of basalt is fluid, it's flowing downhill, and your downhill from here is this way. So, and then you can see that the basalt plateau itself now tilts to the southwest. So the low point on the basalt plateau is right here at Wallula Gap. So what you had was this 10 million year period of fiery catastrophe where you had these huge upwellings of liquid, extremely hot lava coming out of the earth, spilling out layer upon layer upon layer over a period of about 10 million years, down to about 6 million years ago. And then there were more great earth changes, and then about 2.5 million years ago, the geological epoch shifted from the Pliocene into the Pleistocene. And what seemed to define that transition was this beginning of this cyclic oscillation between glacier, interglacial, glacial, interglacial. Now, when you go back to here, imagine that you've got this process here repeating itself, who knows how many times, maybe 10 or 12 times over the course of the entire Pleistocene. Now imagine the amount of geomorphic work you're talking about over a period of just not even just one cycle, but multiple cycles. Now, what do you think survives the onset of glaciers that are this huge? Well, not much. The forming of these glaciers and the growth, the lateral growth of these glaciers basically demolishes anything in its path, right? It just, I mean, what do we find under the glaciers? Well, we find thick layers of glacial till, which is just ground up, pulverized earth, rocks, organic material that was the remnant of forests that maybe once grew there before the encroachment of the glaciers. So under the glaciers, we find huge volumes of this till, it's called. And the till is just nothing but pulverized rock. It has no structure to it. It has no obvious bedding or striations in it. Why? Well, because the glaciers aren't sorting the rock. It's just pulverizing it, grinding it up, like putting it in a big grinder and just chaotically mixing it all together. Water, on the other hand, sorts. So it leaves two different kinds of signatures that you can read in the landscape, right? Glacial till, which is the raw material that forms moraines. A moraine is built of till. The glaciers can take that chaotic till and shape it. Well, so what happens, you have terminal moraine that forms at the snout of a glacier. You have lateral moraine that forms along the sides of a glacier. Let's say that the glacier is moving through a mountain valley. As it's doing this, it's grinding off the sides of the mountains, pulverizing it. That material then falls down and forms thick deposits between the glacier and the mountain. That's lateral moraine. Then let's say you've got two valleys, which is a fairly common thing, come together and they both have glaciers in them. Well, they both have lateral moraine, right? Now, and that lateral moraine is being carried along with the movement, like there are these frozen, slow-moving rivers, is the way to think of a glacier. They're not just static chunks of ice just sitting there, right? They're moving, they're flowing. You have a zone of accumulation at the top end of the glacier where the snowfall on the glacier far exceeds the dissipation of the glacier. And then you have the zone of ablation, which is at the bottom end of the glacier, where the melting and the recession back of the glacier essentially is too great for the glacier to continue to grow, right? And again, just like the lake volume, you're going to have this oscillation. If you've got more snowfall up in the zone of accumulation, the glacier will grow because it's all, you pick up this weight. Picture you've got this weight and it's bearing down. Well, what that's doing is it's accelerating the flow, right? Because that weight, that pressure is making things move faster downhill, right? Now, at the bottom end of the glacier, it's melting, right? And you can go, and if you ever go on any hikes, and you're at the terminus of a glacier, you'll see there's great vigorous streams of meltwater flowing off the glacier. So let's say you have a warmer than usual winter. Well, now what happens? Well, it's likely that the rate of recession, recession is melting, will exceed the rate of forward expansion. On the other hand, increase the amount of accumulation at the top end of the glacier might grow. Now, what have we been seeing throughout most of the 20th century is glacier recession, right? Because of the warming, the glacier has receded, right? So now you've got this situation where you have these oscillations. Picture this now. The glacier is flowing. One of the things that it does is it's moving along. It's almost like scooping. So you've got thick till at the bottom. The glacier is almost like scooping that till, and that till now rides up into the glacier itself. The term is N-glacial, E-N glacial, within the glacier. Superglacial on top of the glacier, subglacial on the bottom. Okay, so now the interior of that glacier is almost like a series of conveyor belts, and it's carrying that material. So now the terminal moraine is going to be a combination. You can think of it as the result of two very much interrelated processes. The glacier itself is almost having a bulldoze effect, right? Piling stuff, but it's also delivering, the conveyor belt is constantly delivering end glacial material at the glacier snout. Now you got two valley glaciers coming down and they meet. And remember, they both got lateral moraine because they're scraping along the sides of the mountains. That material is falling down and it's being incorporated between the mountain and the glacier. Two glaciers meet. So what happens now, and they become one bigger glacier. But you can tell just by looking at a snapshot, without even seeing the zone of confluence, you can say, okay, well, this was two glaciers that flowed together. Why? Because the lateral moraines join, and now you've got lateral moraine on one side, on the other side, and now you've got it down the middle. And that's called the medial moraine. Then, when the glaciers begin to recede back, well, let's say the glacier has been more or less stationary at a point over a period of a number of centuries. It's built a terminal moraine. A terminal moraine can be pretty significant. I mean, it can be hundreds of feet thick. right? Now the glacier begins to melt back and it pauses. So it pauses for a century or two at a particular place and it builds another moraine. Now that moraine may be smaller and typically will be not as impressive as the ultimate terminal moraine, but you can now track the recession of the glacier. So now you've got recessional moraine. So this is some interesting new vocabulary to add. And if somebody listening to this is very interested, is learn these terms, because we're going to be talking about this. You know, if I'm going to be suggesting references to read, you're already going to know the terminology. So let's go through it again. We've got till, which is the material under the glacier produced by the grinding of the glacier over the land. Then we've got different types of moraine. We got the terminal moraine that forms at the snout of the glacier. We've got lateral moraine that forms along the sides of the glacier. We've got medial moraine where two valley glaciers flow together. And we've got recessional moraine where the ice is receding and pausing in its recession, pausing long enough to build secondary and tertiary moraines. Typically, a terminal moraine will oftentimes have an arcuate shape. Let's go through. I think I've got
moraine is the description of when it is deposited, correct?
Yeah, moraine is the structure.
Yeah, of how
till is the material composing that structure.
Yeah.
That's yeah. But here, geologist David Alt wrote a book, which I read not long after it came out. David Alt and Donald Hindman, 1995. This was the Mountain Press Publishing Company. Northwest Exposures, a geological story of the Northwest. So he goes into some of the background, which in some of his ideas I find very interesting. So let's go through this. Several quite different things happened about 17 million years ago. The entire chain of big Western Cascades volcanoes, which had been erupting vigorously for at least 20 million years, abruptly became extinct. Overwhelming flood basalt lava flows began to pour across a vast region of the inland Pacific Northwest. Faults began to break the former plains of Nevada and Utah into the swarm of broad valleys and jagged mountain ranges of the basin and range. And the climate became very wet and warm. Was it a coincidence that all those changes came at once? It seems far more likely that they had a common cause. And what do you think he proposes for a common cause? Before we go on, let's clarify a term. Up here, I think what I'll do, this term right here, faults.
Mm-hmm.
Okay, so whose fault is it?
It's yours, Randall, obviously.
It's my fault. Okay, so a fault is like a big fracture in the Earth's crust, right? You heard of the San Andreas Fault. It's
yes.
like a big crack, right?
Right. It's what I understand faults to be is there's a lot of seismic activity at fault lines, essentially.
Oh, yes. Good point. Now, what's the difference between a fault and a fracture?
I don't know.
Well, you're about to know. And once having known, you will now know this for the rest of your life. Okay. A fracture is just a crack. It's like a static situation. You know, you go in and, crack anything. You got a piece of porcelain on your countertop, smash it with a hammer and there's a crack.
Mm-hmm.
Well, that's pretty much of a static situation.
Ooh, now, can I guess what a fault is?
Yes.
A fault is a meeting point between two different structures versus a crack.
Not exactly. It can be, yes. But what it is that a fracture is simply a crack. It's a static situation. A fault is dynamic. There's movement. There's movement along that crack. And that movement has interesting consequences. Okay. So look at my hands. You can have movement that's this way. We won't get into these terms today. Movement this way. We can have movement this way. And it creates what are different kinds of faults. Typically an earthquake, you can have a sudden, what'll happen is there's stress that builds up along the fault line, and then it'll suddenly rupture. You got an earthquake. It can be this way. It can be this way, right? You can see that there might be cases where there's an escarpment actually formed because you'll have a down dropping or an uplift along the fault line. We can get into talking about that in another episode in more detail. I don't want to get too far afield with that, but that's the basic difference. So faults begin to break the former plains of Nevada and Utah into a swarm of broad valleys and jagged mountain ranges of the basin and range. And we saw that. If I go to the Bonneville flood, so there is the basin and range province that we're talking about. Look at this whole, and notice that it has a circular form to it. I wouldn't be shocked if there was that was some ancient multi-billion-year-old giant crater, on the scale of the lunar Maria, hundreds of miles across, but so old that only just a suggestion of its original circular form. But this is your whole basin and range province, and almost every one of these valleys or basins that you see flat, here's Bonneville Basin, flat, right? Those were lake bottoms. So there was all kinds of lakes throughout here. I did a graphic to show what it would look like if all those lakes that have been documented to have occurred in these basins were contemporaneous. It would look like this. Now you can see that Bonneville is just part of a much larger complex of lakes. Like there's all Pyramid Lake, Lake Lahontan, and other lakes that have had their names given to them. We're not going to go out and talk about that today, but one of the things that we will call attention to is these rivers flowing north like this up into the Snake River. See, here's the Snake River Plain, and we see the Bruno here and the Owyhee here, rivers that are flowing north into the Snake River Canyon. One of the things, my takeaways from this is that I now believe that possibly the waters flowing out of Lake Bonneville, which you can see right here, right here. This whole big basin and range, this was the lowest spillway out of the rim right here. And so when the waters rose, they started flowing over and out the lowest saddle, if you will, within the whole basin and range province, flowed out and then flowed across the Snake River Plain like this, and then up Hell's Canyon's up here. You can't see it. But you have the Bruno River and the Owyhee River flowing up here into the Snake. I now believe, or have enough belief, that I think it's worth testing that there were catastrophic flows to the north through these canyons here that were contributing to the flow, the maximum discharge of the Bonneville flood. And that was one of the things, and we'll circle back to, we'll be getting into that when we start exploring all of the new video footage and images and drone footage and the new LiDAR maps of this whole region. Things that I obviously didn't have access to a couple of decades ago, my first time I was exploring this landscape. But anyways, what I'd like to do is go on here with, let's see, I'll stop share here, and then we'll go on with that quote by David Alt, because it has some very interesting implications to it. And let me go back. Let's see. Here we go. So,
Randall, pull that mic a little bit closer again. Yeah.
Yeah. Okay. So he says the climate became very wet and warm, and this is, in that transition. So we had these. Let's recap. We had these great volcanoes going off vigorously. This was all those big volcanoes of the Pacific Northwest. Somewhere between 17 and 20 million years ago, those eruptions stopped. But then at the same time, you had this overwhelming, as he describes it here, overwhelming flood basalt lava flows began to pour across a vast region of the inland Pacific Northwest. Faults began to break the former plains of Nevada and Utah into the swarm of broad valleys and jagged mountain ranges of the basin and range. And that's what we were just looking at. And the climate became very wet and warm. Well, now, wouldn't it make sense if the climate becomes wet and warm that you're going to start having the formation of lakes? That would just be natural, right?
Right.
And that's what we were talking about earlier, is that it seems like at that point you could have had the formation of a lake in the basin that later became the huge Lake Bonneville. But he says the climate became very wet and warm. Was it a coincidence that all those changes came at once? It seems far more likely that they had a common cause. Had anyone been here about 17 million years ago, they would surely have thought that the course of tectonic and volcanic events in our region was settled and destined to continue so indefinitely. Nothing foretold a radical change. Then, we believe, an asteroid struck near the southeastern corner of Oregon and set the development of our region on an entirely different course, which continues. It was a random and utterly unpredictable event. Astronomers can measure with great accuracy the speeds of the asteroids they see, and they have always estimated, they have ways of estimating their sizes. Given the speed and size of an asteroid, it becomes possible to estimate its energy of motion. That leads to an estimate of how big a crater it will make if it should strike the Earth. The largest craters that exist as open holes are the Manicouagan crater of northern Quebec and the Popogai crater of northern Siberia. Both are about 60 miles across, and that raises a question. Some of the asteroids known to exist in orbits that cross that of the Earth carry enough energy to open a crater much more than 60 miles across. Where are those very large impact sites? If no craters more than about 60 miles across exist, then those larger impact sites must have some other form. It seems very likely that they develop into flood basalt provinces, like the Deccan Plateau of India and the flood basalt province of the Pacific Northwest. That, to me, makes a lot of sense. So when we go back to the big picture that we were looking at a little earlier, looking at that digital map. So look at this area. Now take another look at this area. Back this area up 17 million years ago, and it's sitting here. Now, if David Alton, Donald Hindman are correct, an asteroid struck here about 17 million years ago. Probably was a high velocity, high density asteroid impact coming in relatively perpendicular to the Earth's crust. Now having the requisite density, velocity, and angle to punch a deep hole into the Earth's crust. The result we'll call pressure relief melting. And you have all this upwelling. Now, over the next 10 million years, the plate continues moving because it's being pushed from the east, right?
Mm-hmm.
So it's moving, and it shows the motion. You can trace the motion of the plate by backing up this area right here and moving it back to Yellowstone. And it's still active. It's still volatile, right? If Donald Alt is right, and I mean David Alt is right, and I think he probably is, we had a major impact event, and we don't really see it. right? But when you look at this area up here, yeah, it begins to make sense. It's almost circular, isn't it?
It is,
Right?
yeah.
Yeah. And it's all fractured and broken up with all of these, what are called feeder dikes, and all of this magma that formed all of this up here, all of this down here, all of this down here, all of this basaltic lava is all flowing out of this like some great wound, and it's bleeding. And the layers of basalt that were the first discharges are the thickest, and then the basalt layers get successively thinner as each pulse of lava it flows out in a great flood, drowning the previous. And given that it was a 10 million year process, there might have been many centuries or millennia between successive outflows. Maybe it requires a period of time for the pressure to build up. It reaches a threshold, it releases, there's an outpouring of basalt. So one of the things that impressed me, the second thing that impressed me a lot about the Bonneville flood route is that we talked, I think with, was it you and I, or it was me and John Arthur, I believe that, or maybe we haven't done it yet. Maybe I just gave a private presentation about the Teton Dam disaster.
Yeah, we talked about Teton Dam.
Okay. All right. We talked about the Teton. Did we talk about the fear that was gripping the engineers and things about the domino effect?
Yep.
And what happened instead was that this tremendous wall of water rushed out from the broken dam. It swept down through the canyon, and wait till you see the imagery that we're bringing back. Why? Because here we have an event that happened back in 1976, and we can see all kinds of things that have their counterpart in these much, much bigger events. Even though when you're there and you're at that site of that dam, you realize, yeah, this was an enormous, enormous catastrophic flood, but it's minuscule, for example, compared to the Bonneville flood. And the Bonneville flood was only 1/10 the volume of some of the peak Missoula flood discharges, which were sometimes, some of those were 10 times greater. But here's the thing, that water gushes out, right? While it's confined to a channel, it's moving fast. But if you look at the topography, you'll see that then the channel opens up into this wide, flat basin when the Teton River rises in the mountains, and then it flows out onto the Snake River Plain. So while it's confined to the canyon, it's moving fast. Once it moves out onto the plain, the water spreads out, and it becomes a sheet, and it begins to lose its velocity. With the loss of velocity comes a loss in stream power. If it's carrying sediment, it'll build a fan delta at the point where the water spreads out and slows down, right? So this is how you can trace the movement. Well, what happened, what averted the disaster that had engineers panicking, ready to evacuate the entire population from American Falls Reservoir to the Pacific Ocean, was the fear that each of the flow coming out of the Teton Reservoir would hit the American Falls Reservoir. The dam at American Falls was old, obsolete, needed upgrading. It would almost certainly fail. Then the water volume of American Falls Reservoir would be added to that of the Teton Reservoir. Now you've got double the flow coming down. The next one, I think, was it called the Walcott, Lake Walcott, and there was a dam there. And then this is going to sweep away that dam, and you're just going to have a succession of failures, right? But that didn't happen. Why didn't it happen?
Well, the water was seeping into the ground.
Two things. The water, yes, it turned out that the basalt was porous enough that by the time that flood surge reached American Falls, it had been reduced to a trickle. The second thing is the water flowing over, let's say, a rough terrain, it loses energy the whole way. I mean, so that energy is dissipated through the course of the flood. All you got to do, take a 5-gallon bucket, fill it up with water, go tip it over, and immediately there's a big gush of water out of that 5-gallon bucket, and it spreads out. And as it's spreading out, it's slowing down, and it's losing stream power. It's losing its ability to pick up material, carry that material, transport that material, and dump it somewhere, right? It's losing all of that, right? Well, so now you've got, if we go back and we look at that map from the breakout point of Lake Bonneville up to, let's say, Shoshone Falls, do this. Look up Shoshone Falls on your
Okay. Got it.
go to, put large size images, and then let's look at a few images of Shoshone Falls, because Shoshone Falls is a relic of the Bonneville flood. It was a recessional cataract that was produced by the sheer power of this huge mass of rapidly flowing water. Ooh, look at the, let's see, any one of those. That's the third one. Well, yeah, okay. We'll look at several because you can get a context here. All right, so this has been called the Niagara of the West. It's a hell of an impressive waterfall. Now, here's the thing. You see that butte up on the skyline? Yeah. If you go to the top of that butte, the surface of the butte, that was the pre-Bonneville flood land surface there. Everything below that line has been removed through the passage of the Bonneville flood.
Oh, wow.
Yeah. Oh, wow is right. And wait till you see, you're standing there in person in that environment and seeing that. But yeah, let's go to that panoramic view.
It's the same view there.
Same view. Now, the entire scene in that view from left to right was, well, look, you can see, look, up on the right, you see another butte. Yeah. That's the counterpart. See, those have the same elevation at the top. And that was the original land surface. Everything you see here was submerged under this gigantic, rapidly rushing along flow of water. Now, here's my question. As I'm there for the second time, looking at all this and taking it all in and looking at the LIDAR and the topography of it, I realized, wait a second. This is at least as much, if not more, water than is measured at the breakout point several hundred miles east of here. Well, here's what we know about water flow. It should be dissipating energy. It doesn't appear to be dissipating energy. It appears to be increasing in both energy and volume. Because remember, think about what happened to the Teton flood surge. It's moving across the landscape. And there's a whole number of, as it's moving over the landscape between the water-land interface, there's energy being lost, right? Initially, you have the potential energy, let's say, of just the lake sitting there static. As soon as the dam breaks, that potential turns into kinetic energy. But that kinetic energy is constantly being reduced through the passage. This is what happens while you have your typical flood hydrograph will have a very steep rising limb and then a long tapered terminal limb, falling limb, if you will. Why? If you have a breakout, like a dam breakout, it could be Teton Dam, it could be St. Francis Dam, it could be any number of the dams that have failed that we know. It could be a natural, like an outburst, a glacier failing, which we have many examples of, particularly places like Iceland and Alaska and the Himalayas and any mountainous regions, right? Okay, so now you've got this outburst. So initially, there's a big, rapid, powerful surge of water. Well, that water then begins to lose energy, and it begins to slow down, the velocity diminishes unless of course if you change the gradient, that changes the equation, right? But what you're going to see, for example, with the flow of the snake is you've got a gentle, slowly declining gradient from east to west, right? However, you're still going to have a lot of energy loss between the point of breakout and the landscape we were just looking at Shoshone Falls. Now, I haven't done this. I would like to go back and maybe even partner with somebody on this and look at the physics of the water flow here, the hydrophysics of it. Because of this, there would be no doubt. There's going to be an enormous amount of energy lost in that passage between the 2 points. So that by the time you get to my point, the point I'm trying to make is by the time you get to Shoshone Falls, it should be a very much reduced volume of flow. Yet what we see there actually looks like it's greater than the volume of water that would have been measured at the breakout point. Well, what does that lead us? It leads us to the idea, well, could have the flow from the Bonneville flow been augmented by additional sources of floodwater? And I think the answer is it seems very likely. Okay. So I hope all this is making sense.
It does, yeah. I mean, we've looked at Missoula and the flood area there and the conversions of them in previous episodes as well. So this is kind of piecing together.
Yes, and it's good. I know we're covering some of the same ground we've covered before, but it's really, maybe it's a fantasy of mine that some of the people watching this are really wanting to understand it.
Yeah,
and not
no, I don't think it is a fantasy. It's very helpful to recap and look at these terms and look at the effects over and over again
from different perspectives. Exactly. I mean, that's how you learn. You have to have some repetition. That's a part of the learning process. It's not the whole part of it, obviously, but it's a big part of it. And if you really want to get to the bottom of something, you need to do that. Let's see. I think I'm going to try something here. I'd like to see. Do you have Google Maps available?
I do. Yeah, I got it open right now.
Oh, cool. Open it up and let's look at this region, and then we're going to move on to other parts of North America, because again, all right. So, I see you've got Bruno Canyon. Let's zoom out a bit there.
Okay.
So we can get the big picture. Okay, let's see. We're
Whoops.
We're way down too far south. Go up to the north of Great Salt Lake. All right, so there you got the Snake River Plain. Let's see. Zoom in and let's locate Shoshone Falls. Pan south. Pan. Yeah. Okay. So, you see Twin Falls. That's where Shoshone Falls is, near Twin Falls.
Yeah, here it is.
Now, if you right click, let's say, I believe you for right click. Yeah, there we go. Yeah, right there. You see that erosional complex there of how there's a lot going on there. And right there, Shoshone Falls is just above your cursor. You see where it says shown right there. There's your pretty impressive stuff. So, pretty amazing. Yeah. So that's where I was a couple of weeks ago. Yeah. There's the falls right there.
So that butte has to be.
We'll probably go into Google Earth to see the butte. Ah, there it is. Yeah. Okay. It's amazing. That was a very well-built parking lot, apparently, because it came through. I mean, look at how unscathed it is. It pretty impressive. Okay, so
the parking lot.
Yeah, you see, the parking lot barely got affected by the flood.
Oh yeah,
look at that.
And he would get touched.
So yeah, my tip of hat to the engineers and road crew that built that parking lot. But yeah, look at there. You see that butte up on the up on the horizon there. So this is right here in the area of, there's Shoshone Falls. Let's see if I can, there we go. So the falls is right here.
Yeah.
And you can see the confined canyon. But then you look up here and you see this tributary. You see, look what we got here. What's going on here, and notice this, if we scan out, look here, we can see the pathway very obviously of the overland flow. You see this brown area?
Yeah.
It's brown because there's no topsoil. It's been washed away. So where there's topsoil, there's agriculture. So what you can see here is that there was a flow coming from up here, right, flowing down, and then it flows back to the Snake River right here. And if we zoom in, let's see, we can probably see several areas here where we've talked about this, where the overland sheet flood becomes confined, it becomes focused, it becomes channelized, right? So what we see here is where it's starting to become channelized. And so when you have all of this, when it's in the form of a sheet, that flow is not concentrated, it's diffused. But once it becomes channelized, remember, you've got what's going on here is like a conservation of energy problem. Whatever the energy of that is when it's flowing over miles of landscape, it's going to be basically the same when it becomes channelized. But now that much energy is focused on a single limited zone of the land, right? So now what happens is it naturally becomes much more erosive. And so what do we see here? Look at this. Here's your cataract. So this is a receding cataract. And it's a fossil feature. At whatever point the source of the floodwaters terminated, and wherever it was in its stages of erosion, once the floodwaters stopped, that cataract was now frozen in time. You see what I mean?
Yes.
And nothing since this catastrophic flood has altered this landscape other than just minimally. However, the whole landscape in itself was created probably in a matter of a few weeks. So when we're looking there at the falls and we're looking up at those buttes up on the top, well, pre-flood, there was undoubtedly, I think, a pre-flood Snake River in a valley that would have been way, way shallower than the canyon produced in the aftermath of the passage of the Great Bonneville Flood. And look it up here. You see this area? Let's zoom in here. You can see these cliffs where the water's becoming channelized and starting to cut a new canyon here.
Right.
Same thing over here. Look at this. You see this? So now, hopefully, people are beginning to get a sense of this whole process and the sheer power of this. And what we're going to be looking at and exploring as we go through this series of episodes is we're looking at a region here. If we're talking about Shoshone Falls, we're looking at a local manifestation of this. What people need to understand, though, thinking back to that box, right? Well, one of the big holes in the box is the fact that you had this flood meeting the Missoula flood right there at Lewiston, right? So how do we explain that? Well, at the current explanation, there's no attempt to really correlate. They're unrelated to each other, right?
So
Is that the case? Well, yeah. I mean, they don't assume that there is a connection between the two, and therefore a common cause is not even considered.
Falls outside of the box.
Falls outside the box. But yeah, this is look, man. I mean, look at this. This, in order to create this, you had to have some extraordinary, powerful turbulence.
And how far away is this in distance from the breaking point where it broke out?
We can figure that out. We can do that. Let me get back here. Get this back to the north. We can zoom out. There's Shoshone Falls. Let's start by going the distance from Shoshone Falls to Pocatello. Let's see. Zoom out here. Where's Pocatello? Okay, so here's Pocatello is here. There's American Falls. So I'm going to take my, let's see which one here I want to, let's see, maybe I can, where is my measuring tool? There it is. I think that's it. Show ruler. Okay. So we're going to create a pathway from Shoshone Falls here to Pocatello as the bird flies is, I should change it here. I can quickly do a calculation. It's in feet right now. I should put it into miles. Let's see, paths or feet. Let's change this to miles. Okay. So up to Pocatello, as the bird flies, basically 100 miles. But by river, we're probably looking at 25 or 30% more because it's obviously not flowing. So we got 100 and say 130 miles. Now let me X that, and then we'll go from Pocatello miles, yes, Pocatello down to Red Rocks Pass, which is right about in here. And that adds about another 40 miles by river, probably 50, because, yeah, I mean, it goes down here and then it dog legs over. So let's say conservatively 50 miles. And what was the other number?
150.
150. So, yeah, let's say it's a route 200 miles. My point is that how much energy is going to be lost in 200 miles? It should be significant. Yeah, I mean, I think if you just wanted to say roughly the ballpark, one would think that at least half the volume of the water would have dissipated, or at least the energy momentum of that water would have dissipated, at least somewhat. I mean, how much is going to be absorbed into the basalt itself? Look, if we go, let's do this. I'm going to take this off, go up here, and I'm going to put in into the search Teton Dam. Okay. Here we go. So there's the remnant of the Teton Dam. Whoops. Now, at one point, I need a better way of navigating than my mouse wheel here, but that'll do the job. So there's the remnant of the dam, right? And you can see there's a canyon that was going to hold the reservoir. The canyon if the had been allowed, if the dam hadn't failed and the reservoir had been filled to full pool, it would have reached 17 miles up the canyon. But one of the things you can see here is that here's where the dam is. As you're coming downstream, notice that the depth of the canyon is diminishing. And then look what happens here. So, and look here. Here you can see still effects of the water flow. Look, it dumped sand as it came down here. And you see, why is it dumping sand? Well, it's because as the water is being released from the constriction of the canyon, it's spreading out. So this is like the reverse process of channelization. The water's in a channel, it's confined to the channel, but as soon as it breaks free of that channel, it starts spreading out, losing velocity. As it loses the velocity, it loses stream power, and then you can see that down here it's dumping sand. Because now the water has not have enough power to even carry the sand, you see?
Yep.
And then the river flows down, and let's see, where does it meet? Let's see, where does it? I haven't really studied this too much, so I don't know where is the confluence of the Teton and the Snake. Let's see. That's Henry's Fork. Henry's Fork, okay, St. Anthony. So somewhere down in here, the Teton flows into the Snake. It's not critical for our discussion now, but I am, let's see, let's get back oriented north. Yeah, and you can see that if I come in here, if you drive along Interstate 15, Interstate 15 is following the outburst of the Bonneville flood, which occurred right, let's see. Yeah, here is where the breakout point, right in here. We can actually see the remnants of the big fan delta that's splayed out across the valley right here. See this stuff?
Mm-hmm.
A lot of that came from the carving of this channel here. And off the uplands here. So you've got this right here. You can see that. So before the breakout, this white spot would have been roughly the top of the alluvial delta that's right in here. So draw a line from here up to here, and that would have been continuous, basically. Right? The top of this coincides pretty damn closely with the highest shoreline of Lake Bonneville, called the Bonneville shoreline. And when the outburst occurred, all of this intervening material here is washed away. This butte right here is what's left of that alluvial dam that filled this whole valley here, see, before the breakout. Okay, so then, right now, I think if I recall, there's like 20 to 30 feet of sediment laid on top of the bedrock in the pass here. The bedrock gives us the Provo shoreline. So if you can picture this, look at my hands. It breaks out. It cuts through 350 feet. This thing here is about 350 feet high. This is the thickness of the material, the alluvial material. The water bursts out and it cuts it, and at this level, there's a shoreline. You can see that shoreline on the western flanks of the Wasatch Mountains very clearly, and we got some great new footage and images of those shorelines. It drops 350 feet and then stabilizes at this bedrock sill. And now a second shoreline is produced there, and that's called the Provo shoreline. And you can see the two shorelines very prominently etched into the sides of the mountains. And in the Bonneville Basin, the Bonneville shoreline is over 1,000 feet above Great Salt Lake. Is this making sense?
It is, yeah. I have a question about a fan delta.
Yeah.
Because you've used the term a couple of times, and I thought I was understanding. What is the difference between an alluvial fan and a fan delta?
Well, an alluvial fan just means it was put there by water.
Uh-huh.
A fan delta means it was deposited underwater. So let's say you've got a lake.
Oh, that makes sense.
And the water's flowing in, and it's carrying sediment, and as it
flows into the lake, it is fanning. Okay,
right.
That makes sense.
Well, if you're talking about an alluvial delta, it could be just, it doesn't have to be underwater necessarily.
An alluvial fan.
An alluvial fan, yeah, sorry.
Yeah.
The delta seems to imply that it is underwater.
Into water.
Yes.
Okay.
Yes.
That makes sense. That's clarifying.
Good. I mean, this is our objective, Becket, is that this all makes sense to you.
Yeah. No, it is, and it's starting to make more and more. I mean, it is making sense. Some of the terms, it's important for clarification there, but I mean, what we're looking at there is essentially, if I'm understanding it correctly, then we're seeing the evidence of where the Bonneville flood broke out, and then we were tracing it all the way to Shoshone Falls, where it should have, by that point, had less velocity and not had as much...
Less power,
not had as much ability to tear up the terrain, but it seems like it had a lot more power at that point.
Right.
And we're looking at the evidence of that and kind of connecting pieces of the big picture. What we looked at is, in previous episodes, was where Uh, Missoula flood, the Missoula flood met with the Bonneville flood, and that's at
Tammany Bar.
Tammany Bar. Yeah, exactly.
Yeah. So there's a lot of unanswered questions. Now, so we've been talking about the Missoula. Of course, I mean, there's a whole lot more we could be looking at there. And at some point, we're going to come back to that. The reason is the Missoula floods represent some of the most spectacular mega flood sculpted landscapes on Earth. Now, what I came away with the impression from the Bonneville is I'm looking at that landscape by Shoshone Falls, and I'm thinking, this isn't that much less than some of the incredible erosional landscapes I've seen as a result of the Missoula floods. So, I mean, this looks to me like it should be more water than the breakout point 200 miles east of here. So, I mean, I've got some study to do. I'm not claiming to have answers or figured out. I have questions more than I have answers for sure. But then we start looking beyond the effects of these two floods, and what do we find? Is we find floods, evidence of mega floods all over the damn place.
Yeah, we talked about, I don't know if this is a good time to bring the Shenandoah up, but I think at the same time that you were in Bonneville, I was driving through the Shenandoah River Valley, and essentially the Shenandoah River flows in between the Blue Ridge Mountain and then the Allegheny Mountains. And it flows right in this massive channel in between them with very similar peaks on both sides of it, which could be.
Okay. So, just as I predicted, now, when you brought this up to me the other day, I've looked at a couple of dozen rivers. I had not looked at the Shenandoah, and I'm looking at it right now. We'll take a look. We got all the signs of an underfit river.
Yeah.
We've got the modern river, which is small relative to the larger channel. We've got an alluvial bottom to the channel. This is all undoubtedly flood stuff. Let's see if as we look through here. Oh, yeah, I mean, look at this. We've got terraces. The modern floodplains of a lot of rivers are relics of the ancient water flows. But let's see. Yeah, look at here. I mean, there was once a flow of water in here. This was one bank and this was the other. So absolutely, look at this. No question.
And for everybody who doesn't know where the Shenandoah River is, you want to zoom out, Randall, and show where this is.
Well, it sits right on the edge of the Valley and Ridge province.
We're in, the complete other side of the United States of America.
Oh, yeah.
This is in Virginia. Yeah.
Yeah, and there's Jim's Country Store.
That survived.
It survived, yep. So this is an example.
And once you see it, I mean, I think it's a good testament to your teaching and what you've been saying is we want people to be able to identify these things. Mm-hmm. Just driving through, beautiful drive, first of all. It's a beautiful route to drive. Just driving through this valley, I'm curious, and I'm sitting there pulling over on the side of the road. It's like a 5-hour drive that Dora and I were on, and I'm looking up. And I'm looking at Google Maps and just trying to find evidence of this because as you're driving, you can see these two peaks beside you and this road that we're in. And at some points, and sure enough, there's evidence everywhere.
Oh, yeah. I mean, once you begin to see it, you can't unsee it. And then you begin to realize it's everywhere. It's everywhere. If we go back, let's see, where was I just seeing that? Some of these areas in here. There was one place particularly where you could see the almost scabland-like features.
Yeah.
But of course, the thing is that in Virginia, a lot of that it's not going to be as obvious, right? Because you've got forests, you've got fields, you've got all kinds of stuff that it's a different post-flood environment, which makes it much harder to recognize.
You start to get some very interesting structures as well in the cave systems. Like there's major cave systems all along this route.
So look at this, a quarry. Now see, what'll be happening now in the future, you're going to be driving through there and you're going to be going, Dara, oh, there's a quarry just ahead. We got to stop and check it out. Why? Because this tells stories. You go into these quarries, and I've been in a dozen of them now. You go in and you talk to most of the time they're happy if they're not in the middle of something to take you out. You might have to wear a hard hat. You go out and you can begin to see stuff. And, that's the next step of this kind of a educational process, is learning now how to decipher and read these deposits. Because oftentimes, see, what happens is, those deposits have been transported. They've been transported a mile, 10 miles, 100 miles. You don't really know. But what you do is you look at the deposits, and then you look at the regional bedrock lithology, and that gives you the provenance. So the lithology is the type of rock, and the provenance is where the rock came from. So if you've got a rock there that came from such and such a river, such and such distance away, well, now you know that the flood came through there, don't you?
Mm-hmm.
Because the flood is picking up stuff locally, which could vary from place to place. It's transporting it along, and then it's dumping. So you can say, well, this type of rock exists, this bedrock exists, this particular type of limestone rock that we see here exists 100 miles to the east up in this particular river valley. So the flood came through that valley, and it picked up that rock and carried it down somewhere and then dumped it downstream. And so when you go to a quarry like this looks like a pretty major rock quarry. So again, the very presence of a quarry means that this is probably a gigantic gravelly delta right here. I mean, look at this. So it looks like you probably had tributary flows coming in through this area. Look at this right here. Doesn't that look like a recessional cataract?
It does.
It sure does. So you probably had a major flow. There's no real river flowing in here now, but at one time there was a flow through this trough right here. It channelized and began cutting this long linear canyon here. It was a receding cataract, and then when the flows stopped, that cataract is frozen in place where it's basically been for 12 to 15,000 years or whatever, whenever the great flows came through here. Harper's Ferry, interesting place. You've got a breach right through the mountains here. When you look at this whole Valley and Ridge province, is amazing. And you've got these water gaps and wind gaps all throughout here, where you'd think you've got these ridges and you've got these troughs. You would think that once a river became entrapped within a trough, it's going to stay in that trough, right? But we got places like, right here. Here's a gap. Let's find one where, while I'm doing this, why don't you look up water gap?
A gap or pass in a mountain range where a river or stream flows.
Do we have any? I found a good example of one.
The Potomac water gap is one in the Shenandoah.
Yeah. You got a picture of it?
Yeah. Here's Harper's Ferry.
Yeah, and what it's doing right there, right where it says Harper's Ferry, the river is just cutting through a mountain range.
Here or here?
No, go up where it's, look at the H on Harper's.
Uh-huh.
And now follow that upriver to the west, all through there. See, it's cut that channel across
Oh,
the
yeah.
mountains.
Oh, okay. I see.
Now let's go to some imagery. So basically, you've got that range, and the water is flowing through. Now, why is the water flowing across this upland area and not just staying confined to the trough that it's in? Well, the assumption is here's the model. There was an uplift. You had compression. Look at my hands here. You have compression east to west across that valley and ridge province. So what happens? It causes. Let's see. Maybe I can do it with a. Not. I need something a little stiffer than that. Here, I'll just use this. You have compression. What does compression do? Causes uplift, right?
Bulge.
Now let's a bulge. Yeah, let's say you've got a river flowing over the land surface, right? Now let's say the river is flowing east to west this way across the land surface, right? Now, I start creating a bulge. One would think that as that bulge is rising, the river would be deflected and stay within the trough. So I've got a trough on this side and a trough on this side, but for whatever reason, there's been this compressional bulge uplift, but the river cuts through it. Well, the assumption is that, then the rate of uplift must have been almost exactly the same as the rate of downcutting, the incision rate of the river. So at the same rate that the bulge is going up, the river is, because remember, now the river's flowing here, so now the bulge starts, but the ability of the river to downcut, to incise through that uplifting bulge is essentially the same as the rate of the uplift. And they have because look, if the uplift was too fast, well, the river is not going to it's not going to cut through it, is it? It's going to be diverted into whatever. If you look at the valley and ridge, you're going to see that you've got all of these narrow channels, narrow troughs separated. That's what's called the valleys and a ridge.
Mm-hmm.
So if you've got an uplift in the creation of the ridge, the river, it would seem like, should then be confined to a valley.
So it
right?
would be, it seems like it should be redirected. So it runs
Yes.
parallel in the trough beside the bulge.
Right. But it doesn't. It cuts across the bulge. So the assumption is that the rate of uplift does not exceed the rate of downcutting of the river, or even more precise, that they're pretty much the same. Right?
Mm-hmm.
Does that make sense?
It does make sense. The
Does
one
it?
thing that's unclear to no, it does make sense. The thing that's unclear to me is if it is bulging, so it's bulging up like this.
Mm-hmm.
Are the rivers, if it's bulging up like this, wouldn't the rivers be running like this to create that bulge? How would they then like turn perpendicularly and cut? I must be thinking about it incorrectly.
No. That's exactly, no, you're honing in on what the problem is, see? Now, we have three scenarios. The bulge is faster than the river. The river is constantly eroding its channel down, right? Now, if we start uplifting, if the uplifting is faster than the river can cut down, well, clearly the river is just going to be diverted along a valley. It's not going to flow up and over the ridge. If the river is cutting down faster than the uplift, well, then the river is just going to stay confined. So if the river is down cutting faster than the uplift, well, now we assume that the uplift is happening and the river is able to cut it faster, right? So the river is going to be cutting a deeper channel through that ridge.
Mm-hmm.
you have to think through this process. Like, how do you get, see, here's the basic problem. The river is flowing in a valley. I mean, we can see this very clearly. It shows up very clearly if you go down to Chattanooga. Okay, so take a look here. Now, look at, you've got the Columbia, the Cumberland Plateau here. Now look at here comes the Tennessee River down here.
Yeah.
Well, you notice that the valley just keeps going, doesn't it?
It does.
You can follow this valley right on down, right? You get down here to this lake. But the river doesn't follow the valley. It cuts right across the plateau. It cuts across 2,000 feet of higher elevation and then comes out on the other side. And then it gets caught in this valley over here. See that?
Yeah.
So now it's confined to that valley. The problem is this. Why does the water cut through here and not just stay in this valley? Well, the working assumption is that the uplift of the plateau is occurring basically at the same rate as the river is incising its way into the surface of the ground.
But still, that doesn't explain why it doesn't follow the valley.
Correct. That's what I think as well. Right?
Right.
Okay, now, I'm going to show you something. I'm going to zoom out here. Let's say I can zoom out, go out to the Missoula Flood, and I'm going to go to a place called Devil's Canyon. Let's see where we're at here. Okay. You see this right here?
Yes. Same deal.
Devil's Canyon. It crosses the upland. So here's a trough and a valley, right? And in fact, this is the valley of the Palouse River. Look over here. If I pull over here and I zoom in, you got the Palouse River, right? Now, clearly, the Palouse River is very small compared to this scoured out trough that it's flowing in. Well, right here, 26, then to 261, follows the path, the original path of the Palouse River. So the Palouse River came down, it flowed through where Washtuna is now, Sperry, Calouse, Estes, Sulphur, flowed down here, right on down, and somewhere right in here, it flowed into the Columbia. It was a tributary to the Columbia. We don't know exactly where. Why? Because these gigantic floods that came down to Columbia have obscured the area of original confluence of the Palouse and the Missoula.
Mm-hmm.
But when we go up here, go back up here to this, we see, what does the Palouse do? Comes in here and it doesn't follow its original channel. It suddenly has been diverted in this almost 90-degree turn to the south, and it now flows down and enters the Snake down here. So we have two instances here where the floor of the valley up here is lower than the upland ridge, and which is considerably higher than the valley of the Snake. We go over here to Devil's Canyon, same thing. Here, you're going from here, you're going uphill to here, and then you're going downhill to here. This is a ridge in between. Now, look at Devil's Canyon, and look at this thing right here. Well, you've seen many things like this now. Look, this is like a recessional cataract right here. So you had water flowing over this. Huge volumes of catastrophic water. So much water that it backflooded all the way down here to Lewiston, Idaho, right here. Backflooded all the way. This is a huge fan right here. Look at this whole thing right here that Clarkson is built on. Then you get down here, and here's where your Tammany Bar is. Here's where Tammany Creek is, and we can go up in Tammany Creek. I've done this, and you can find the backflood slack water silts dumped up here in the
we've looked at some pretty good pictures of that.
Yes, we did. And so we know we know where that silt came from. right?
So the cutting, the water gaps are.
So, okay, so let's put this then into perspective where we're going with this. Where am I here? Lewiston, let's get back to where we were at. Where were we here?
We're talking about Devil's Gap.
Yeah, here we are. Okay, Devil's Canyon.
Yeah.
Okay, so what we have here is we have a down cutting right through it, like it's been sliced right through this up higher land surface. Well, this didn't happen because there was a river here, and this particular piece of land rose at exactly the same rate that the river was down cutting. No, this was cut because you had this gigantic flow of water that overwhelmed the pre-flood watershed divide, which was this upland area here. So you had a two watershed divides here. You had the Palouse River coming here. You had the Snake River coming here. They're separated by this ridge. In fact, we could even, we could go to Google Earth and find out exactly what that change in elevation is. And I might just do that just for a good laugh.
So the direction of the flow, and the power that it's moving at, essentially, it took less energy to cut through the mountain and create that canyon than it would to divert it.
Well, what happened was you had so much water coming from the north. Let's go to the, here you can see the pathway of the water flow right here. And look at it. It's coming down. You see this dark area? That's where all of the lush topsoil has been washed away. And we're basically down to bedrock right here. You can see it comes down, and here's this diversion right here. Right? Well, this was entirely the product of the flood. Well, for one thing, what happened was, if you look at all of this, this is all thick layers of alluvium. There was so much alluvium dumped in the pre-flood channel of the Palouse River that once the huge water flows were over, it created a dam, a natural alluvial dam right here. And that caused the water to divert. So this diversion of the water here was the result of two things. The overflow cut this channel, and it probably is following a fracture, a weakness in the bedrock. That's why it's so straight like that. Right? And that's what water does. It's always looking for the least resistance, the weakest point. Yes. And that would have been the same thing that would have happened down here at Devil's Canyon.
So once it finds that weakest point with the overflow, there's too much water for it to keep going in the direction that it's going. So once it finds that weak point, it's going to divert to that.
And that's what
at least
it did
some
in
of
this
the
case.
water. Yeah.
Yeah. In fact, most of the water here. Because look, this is now the pathway. So the Palouse River was completely diverted by the after effects of the flood. Down here at Devil's Canyon, the overflow of the water cut the canyon, but because the Palouse River was completely diverted to the east, there was no water. There's no water flowing through Devil's Canyon. So what we have here, in a sense, is a water gap, because the water is still flowing through the gap. And here we have a wind gap, because only the wind is blowing through that gap.
Today, but it was created by water.
But it was created by water. Now, I would argue that we should consider that the water gaps and the wind gaps that we find in the Valley Ridge province were produced by the same mechanism, by the ridges being overtopped by gigantic floodwater flows, those flows then cutting the channels down. And then once the floods were dissipated and over, the modern rivers are following. And in the case of there by Chattanooga, that overflow cut that winding incision into the Cumberland Plateau down to the level of the valley floors on either side. And then when the floods were over, the Tennessee River now flowed through that catastrophically cut channel. I'm saying that we should take a new look, a relook at some of those phenomena that we call water gaps and wind gaps throughout the Valley and Ridge province of the East. And I will make a prediction that at some point in the future, geologists are going to acknowledge that these features were cut by catastrophic water flows and not some long, slow process, that it was so slow you wouldn't have even be able to see it happening. And it just so happened that the uplift of the ridge was equaled by the downcutting of the water flow. Hopefully that's making sense.
It does, yeah. It makes a lot of sense.
Because if that's the case, then, you know, what happens to our box that we looked at?
It gets smashed.
It gets smashed. That's right.
Yeah, it doesn't even get bigger. It gets completely smashed. I guess if you want to look at, just keep making it bigger and bigger and bigger at all times, then you can.
So,
yeah, well, if it doesn't make sense, I guess to address the audience, it's making more and more sense to me, which is kind of the vehicle that we've been presenting this information to, but if it's not making sense to y'all, leave the questions in there and the premiere, if you're watching this, or leave them in the comments, and we can poll these and do Q&A episodes as well, where there's questions that have been built up. I think that'd be awesome. I think it'd be cool to get some more questions from the audience as well, and maybe do some live Q&As and have some more interaction with people who are learning this material like I am.
Well, and you know, I don't have the final explanation, not by a long shot.
Tell us, Randall, please.
But I have been asking questions about all of this for about 40 years. And I think I've got some answers, not all the answers, because see, here's the problem I run into, is that you think you're starting to get a handle on it. You're starting to get some kind of at least a hypothetical framework in which you can think through it. And just when you think, okay, I think I'm making sense out of this now, suddenly the bigger box, the sides of it blow out. And see, now, I mean, for me, I've gone from regional to, you know, the scale of maybe whole states, then to a scale of a whole continent, then to the scale of the whole planet. And of course, just when I thought, okay, now the whole planet, I'm realizing, no, if we're going to be thinking about this and really come to a full realistic explanation, we have to expand the box even beyond the planet, because Earth is part of a much bigger ecosystem. And I think that what we're seeing, a lot of these gigantic phenomena and the after effects, are the result of events that have transpired on a, shall we say, a trans-terrestrial scale.
The big picture, it keeps expanding.
Yes. So we've learned the term underfit river.
Yep.
We've been going for, what, a couple hours now?
Almost three.
So we should probably call this an episode. I'm not going anywhere other than Cosmic Summit, which we should probably mention. The Cosmic Summit's coming up in 3 weeks.
Just a little bit less, actually, in 19 days from the day of recording. So it'll be 2 weeks from the day that this is released.
Now, is there going to be anybody talking about the great mega floods? Planetary
yes, I believe there will be somebody who's talking about mega floods. And if I'm not mistaken, that person is Dr. Dallas Abbott from the Comet Research Group. Mega tsunamis.
Good. Okay, so awesome. And wait, she's talking about primarily tsunamis, right?
Mega tsunamis, yeah.
Mega tsunamis. Oh, yeah, I can't wait for that.
Yeah, she'll be on that Saturday in the morning.
Yeah, because I thought, wait a second, is George getting somebody to talk about mega floods that I don't know about? Who supposedly, why would you get somebody to talk about hey, I'm the guy, George, okay? But no, Dallas Abbott is, yeah, I got inspired by her work, God, I don't know, 20 years ago, at least. Yeah, I'm definitely looking forward to what her presentation is. And see, mega tsunamis, that's another part of this whole equation, and a really important one.
Yeah, it's very interesting. And I've heard her mention Madagascar as well. We looked at that, I think, in the second episode we ever did.
I think we did, yes.
Yeah, or second or third.
And was referencing her work.
Yeah.
I want to make it clear that she's the one who found the evidence for the Berkel crater and has been mapping the mega tsunamis. And that is that is an integral part of the whole, the whole complex of data that we're trying to put together to understand the catastrophic history of this planet that we live on. And what to me is so interesting is that, I find looking at the 5 great mass extinctions, the Cretaceous Tertiary, which is now the Cretaceous Paleogene, but that's a 66 million year ago event that terminated the reign of the dinosaurs, right? It is of tremendous interest to learn more about that. But I think you could make the argument that it's primarily more of academic interest because 66 million years ago, absolutely it involved the great pageant of life on Earth, and to the extent that that life on Earth and the evolution of life on Earth led to the appearance of hominids, and then of the 15 or so species of hominids that we know about, Homo sapiens sapiens came along and we were able to create rocket ships to go to space, right? I don't know of any other species of hominid that has been able to do that. I don't know if Neanderthals were being able to build rocket ships to go to the moon or to Mars or anywhere else, right? So here, I guess the point I'm trying to make is that it's one thing to talk about something that happened 66 million years ago. It's something else to talk about something that happened 12 or 13 or 14 or 15,000 years ago. Why? Because,
affects modern history.
Yeah. So the youngest date I've now seen, and I'm not sure about this date, but I'm going to use it anyway, 14,600 years ago, date for the Bonneville flood. Some dates put it older than that. 14,600, though, intrigues me very much because that's pretty much exactly the date of meltwater pulse 1A. And the transition into and out of the older Dryas, which is something we want to take that whole span of time and look at it in more detail at some point. Because we're getting to know a lot about the younger Dryas, we know lesser about the older Dryas. And then what was between the older and the younger Dryas, right? There was some very interesting climate stuff going on there. But meltwater pulse 1B is 1A is dated at 14,006. And some of the younger dating on the younger edge of the dating spectrum of the Bonneville flood puts it at about 14.6, which would kind of make sense to me. But 14.6, let's divide that by 25. And we're looking about 580 generations ago. 580. If your generation is 30 years, I use 25 years for a generation, right? If we divide that by 2, we'd get the number of presumable lifespans, which is about 290 lifespans. But double that, you get the number of generations. But those people were our ancestors. Now, I have not traced I don't know how far you've traced your family tree back. I've not traced mine back 590 generations, but I'm working on it.
Oh, yeah, I'm sure we all are.
I want to know what my great-great-great-great-great-great-great-great-grandparents were doing during the younger Dryas.
Well, you let me know because they'll probably be the same thing.
Probably. But yeah, so we're going to continue this because there's a lot of things. Let's see. Knowledge ultimately is an integrated body. It's not, here's this thing, here's physics, here's chemistry, here's geology, here's hydrology, here's archaeology. Like, they're not each in their own separate camp with walls between them, right? We have to be able to talk about geology if we're going to talk about archaeology, right? And see, the thing is when we're looking at the last 12,000, 13, 14,000 years ago, there were people then, and these people had lives, and they were doing stuff, and they were presumably as smart as we are today. There's no anatomical evidence to indicate that they didn't have the same brain capacity as us and the same ability to think, right? However, we know something is different. We know that those final stages of the late glacial maximum, there was some pretty significant and constant extreme alterations in the global environment and climate that we haven't had to deal with for 10,000 years. So in a way, when you compare the Holocene, the last, say, 10,000 years to what preceded it, we've had some pretty quiet times, pretty easy times compared to what our ancestors would have had to been able to survive. As a result, with, of course, lots of modifications and interruptions, we've been able to build civilization that we're enjoying now. How many aborted efforts have there been since 10,000 years ago to plant the seeds of civilization and build an enduring civilization? Probably quite a few. Another thing that we need to talk about. But the point is that we see that in the Holocene, there are dynamic changes, not on the scale if we go back to the late Pleistocene, but certainly enough that some of those events, the Bronze Age collapse, for example, the onset of the neoglaciation, the 8.4-year, 200-year extreme global cooling that took place right in the middle of the climatic optimum that immediately followed the end of the Ice Age. Any one of those events would put severe stress on our own civilization today. And this is something we need to take into account, because if we're thinking that carbon dioxide is the sole and dominant control knob for the climate change, we're missing a whole bunch of variables in the equation. And if we're going to understand, if we're going to use that equation to try to make any kind of predictions of what we might be facing in the future, and we leave out all those variables, no, our equation is not which then is the basis of our computer models. They are not going to reflect reality.
Mm-hmm.
And I'm afraid that with the politics invading the science of climate change, which is exactly what's happened, it's been hijacked. It's been hijacked to the service of a political agenda, and we're not getting the real story of climate change on Earth. But everything we're talking about here, when we're talking about megafloods, I mean, it should be obvious from anybody who's listening with an open mind that we're clearly talking about climatic and environmental changes on a scale far beyond anything we've experienced, say, since the advent of modern science. But they're very real. You know, when we're talking about the Bonneville flood or the Missoula flood or the onset of an ice age, the termination of an ice age, we're talking about climatic changes on a scale outside the range of anything we've experienced in modern times. In the same way, when we look at those gigantic river valleys and we see the modern rivers flowing in those valleys and understand that, no, this is not the byproduct of millions of years of slow erosion. No, the modern rivers are occupying gigantic valleys because that's the logical place. In the post-flood world, obviously any water flow that intersects these huge river valleys is going to get captured by those river valleys, and they're going to stay until another flood with the requisite capacity comes along. Then you could have perhaps the filling of that valley, the overcutting of the watershed divides, just like we were talking about, and the establishment of a new river channel. I just showed you an example of how, in the course of a catastrophic flood, a river was diverted into a new channel. But what did it take? That Palouse River flow pre-flood probably was many millennia flowing through that valley. One event, probably within a matter of a week, a month, something in a very short range, completely altered the pathway of that river. And now it's been occupying that new channel since the flood was over, 13, 14, 12, 15,000 years, whatever the exact date ends up being. So we have to begin to understand that the uniform gradualistic model is only half the explanation, and that slow incremental changes that we see, that we can certainly see over one lifetime. I mean, I've seen, I regularly monitor nearby creeks near where I live and have been doing it for decades. And yeah, there are noticeable changes that occur. The channel, one of the creeks that I walked by, the channel is probably shifted by 50, 60, 70 feet from where it was the first time I walked along the edge of that creek, 30 years ago, right? Interestingly, the changes in that alterations was the result of basically just two events. Two events did more geomorphic work on that creek channel than all the rest of the 30 years of change combined.
Mm-hmm.
And it did it within like 2 days for each of those events. And I think that's the model we need to look at and understand that this planet is subjected to these outsized events that completely alter everything. And if there happens to be a civilization somewhere in the mix, we're talking about reboot. We're talking about we're starting over again. We're back to the Stone Age. We got to start over. And we pass down legends and myths to preserve the memory of those events that had such a profound effect on our human life on planet Earth.
Level 1.
Yeah. So I think that's maybe where we should leave it for this episode. But there's a lot more to cover in this, and I hope people stay with us.
Yeah.
Because I can tell you this, it does not get any less interesting as you go forward with it. And people need to know, hey, this evidence, you don't have to travel far to find evidence once you know what you're looking for.
Just look around.
Let's look around.